Hello, these are the Calculus Quiz 9 review solutions. So firstly, we have 10 questions where we're asked to determine the limits for some end behavior of this function. So in most cases, we'll have a limit in these problems that does exist because the function tends to go somewhere else. So the only case where it would not exist would be for some vertical asymptotes. So we'll be keeping an eye out for that. So getting right into it, question number 1 has just a polynomial function. So remember, for a polynomial function, our end behavior really is dictated by the largest degree term. So for us, that is this negative x to the fifth. So if I'm plugging in negative infinity, so since this is an odd function, I would have a negative term, and then I have a negative infinity that I'm raising to an odd power, which turns out to still be negative, so this ends up being a positive infinity. So this limit actually goes to positive, or is positive infinity as x approaches negative infinity. For question number 2, we again have a polynomial, but we need to do a little work to figure out the highest degree term. So going through this, I need to know sine, and I need to know the degree of that highest order term. So I'm going to say, all right, we have negative x squared times. We have negative x, and we cube that, so that is going to simplify out to essentially be negative x cubed. Then we have 2x squared, so this is all that we care about, positive and squared. And for this term, we have negative 2 times x to the fifth, so negative x to the fifth. So putting all of these together, I have 3 negative signs, so overall my term will be negative. And then I have x raised to the 2, 5, 7, 12. So it's raised to an even power. So when I plug in infinity to this, I have something that is going to be infinity to an even number here is going to be positive, and then times a negative. So my limit ends up being negative infinity. For question number 3, looking at end behavior, now I have a rational function. So I'm going to look at whether or not the degree of my numerator is greater than, less than, or equal to the degree of my denominator. So here, m, which is the degree of my numerator, is 6, and the degree of my denominator is 4. So in this case, the numerator is a higher degree than the denominator. So in this case, all I really need is to look at the signs of my denominator and figure out whether or not it will be positive or negative. And then I need to see if my numerator will be positive or negative, because we know that this will go to some kind of infinity. We just need to know if it's positive or negative. So in my numerator, I would have negative times a negative infinity raised to the sixth. And in the denominator, I have a positive negative infinity raised to the fourth. So my denominator works out to be positive, essentially. We'll just say it's positive infinity. And my numerator also works out to be positive infinity. Now this is positive infinity to the fourth, this is positive infinity to the sixth. So my numerator grows faster than my denominator, which means that my actual limit is positive infinity. For number 4, we again have the same case where we need to compare degrees of the numerator and denominator. So in this case, my numerator has degree 2, while my denominator has degree 3. So in this case, m is less than n, and if I look at this, I will have positive infinity squared in my numerator over negative infinity raised to the third. And so this is the same as infinity squared and then negative infinity cubed. So here my denominator grows faster than my numerator. So in this particular case, the limit actually is 0, because the denominator grows faster than my numerator. For question number 5, again, I need to make sure that I'm looking at the highest degree term. So in my numerator, I have negative 6x to the fifth. In my denominator, I have 9x to the fifth. So these are both the same degree, which means now I need to look at coefficients. So I have negative 6, and then I have infinity to the 5th, over positive 9 times infinity to the 5th. So the infinities to the 5th essentially cancel out, and I am left with negative 6/9, which simplifies down to negative 2/3. So my limit in this case is negative 2/3. So just to recall, these are all very similar to just horizontal asymptotes. So now we have exponential equations. So never mind about number 6, I guess we're just not doing it. So we have several different things going on here. Essentially what we're going to do is we're going to break this apart and deal with it one piece at a time. So we have 1.1 as the base for an exponential equation, and we're raising it to the x squared plus 8. So if I'm plugging in something that is going toward infinity, I'm just thinking, okay, it's negative infinity as the power, and then I square that. So this is essentially the same as 1.1 to the positive infinity, and then we don't really care if it's squared, but it's really big. It's going toward infinity. And so we also have a negative coefficient. So we have the negative coefficient, and then we have an 8 here. So I guess the real question is, what happens to this 1.1 as it's going up to a higher and higher power? So since this base is greater than 1, as it's raised to a higher and higher power, this tends to go to infinity. So 1.1 to the infinite power is essentially going to be infinity. So all we need to do is say, all right, well, if it's negative, then this must be negative as well. So the limit here is going to be negative infinity. So for question number 8, we need to do the same process. So I have e. Now, in case you've forgotten, e is greater than 1, and we're raising this to the negative x cubed plus 100. Now, we don't really care about the 100 since we have an x raised to some power here, but we have negative x, so instead of x, let's pretend that that is just infinity, and we're raising it to the 3rd power. So we're raising it to the negative infinity power. So what does that mean for us? Well, this e to the negative infinity is the same as 1 over e to the positive infinity. Well, e to the positive infinity is a really big number, so this is essentially 0. So that means that as x goes to positive infinity, this whole thing here goes towards 0. That means that all that's going to be left when x goes to infinity is this negative 5. So our limit in this case is negative 5. For number 9, we have now a little bit more of a fraction, but we're still just going to look at this exponential part first. So we have 0.75, so all of a sudden we have now a base that is less than 1, and we're raising it to the negative 0.5x. So we don't really care about the 0.5 too much, but we do care that the x is negative. So when I go to positive infinity, and I plug in a positive infinity, I'm raising this to the negative infinity power. So this is pretty much the same as, or this is the same as, 0.75 raised to the positive infinity in the denominator. So when I have 0.75 raised to the positive infinity, that means that this whole thing here, this denominator, essentially is going towards 0 because I have a base that is less than 1. So this is going towards 0. So that means that this whole thing right here is actually going toward positive infinity. Now, it would be positive if I had not forgotten the fact that this has actually got a negative coefficient. So this is negative, which means that this right here is actually going toward negative infinity. So I essentially have now 1 minus infinity in the denominator, and then I have a 10 in the numerator. So what does that mean? Well, this whole thing here is going toward infinity, so I have negative infinity in the denominator and 10 over here, so that means that this is actually going to be 0 because my denominator is blowing up. My denominator is going toward infinity. So that means that it's much larger than my numerator. Now, for question number 10, we have a limit where we have our exponential in the denominator. And so our exponential is 1 minus x squared. And so if I'm plugging in infinity here, and so it does have a positive coefficient, so we'll leave that there as well. So I have 1 minus a negative infinity squared. So I have really e to the negative infinity squared. And so that is the same as e to the negative infinity. The square doesn't really matter in the end. So e to the negative infinity, which is the same as 1 over e to the infinite power, is essentially 0. So this whole thing right here goes to 0. So what's left is pi squared over negative 2 pi. So now I can just do a little simplification. So one of my pi's will cancel out, and I'm actually just left with negative pi over 2. So there's a little algebra at the end of this one. So again, for exponentials, really just work through it slowly and say approximately, okay, what does it mean to plug in an infinitely big or infinitely negative number in our exponents? Okay. For questions 11 through 13, we're going to be using a table of values. And so you can use either your calculator or you can use the Desmos app online to determine the limits as it's described here. So I'm going to, in my calculator, write in y1 equals ln of 1 plus x over x. So I'm going to go do that right now. And then I'm going to go into my table. I'm going to make sure that I am in ask mode. So when I plug in the actual limit, so actually here's what my table looks like. So I have x and y1 columns. When I plug in the actual limit, I'm going to see that I end up with an error. So that means that my function does not actually, or is not actually defined at x equals 0. So what I'm going to do is I'm going to test two values on either side of 0 that are really close. So for instance, I can test negative 0.001 and negative 0.0001. And then on the opposite side, I can test the positives of this, 0.001 and 0.0001. When I do that in my calculator, I get the following values. So my calculator tells me that this negative 0.001 gives me 1.005, and the negative 0.0001 gives me 1.0001, which is a little rounded, I imagine. And on the opposite side, I have 0.9995 and 0.99995. So it appears that these values are pointing us toward an actual limit value of 1. So I'm going to record my limit as 1 because these are very close. They're approaching a value of 1. So going on to number 12, again, I'm going to say, all right, y1 is equal to cosine of x over, and I'm going to make sure I use parentheses here, x minus pi over 2. So again, I'm going to go into my table, and I'm going to set it up. So my x column and my y1 column. And when I plug in pi over 2, I will get, again, an error because my function is not defined there. So now I need to be a little creative about how I plug in these values. So I'm going to do pi over 2 plus, actually let's do the minus side first. We'll do minus 0.01 and then pi over 2 minus 0.001, and then I'll do the opposite to get the other side. So I'll do plus 0.01 and pi over 2 plus 0.001. So this is perfectly acceptable. Your calculator takes these inputs just like it would anything else. And so when I do that, the values I get for y1 are the following. So I have negative 99.96, negative 999.6, and then I have 99.962 and 999.62. So here it appears that as I'm getting closer to the x value of pi over 2, on the left side I'm going insanely negative, so I'm approaching negative infinity. And on the right hand side I'm getting insanely positive, so I'm approaching positive infinity. So in this particular case, I have kind of a diverging path on either side. So that means that at x equals pi over 2, we actually have a vertical asymptote, and we have a negative infinity limit on one side and positive infinity on the other. So that means that the actual limit here does not exist because they do not approach the same thing from both sides. So finally, going on to 13, we have a little interesting case because we have x is approaching negative infinity. So again, I'm going to try to use a calculator here. So I'm going to go in and I'm going to say y1 is equal to this whole mess. So x squared minus 25 in a square root minus 5 over 2x minus 10. So be careful with your parentheses here. And I'm going to go into my table, and I'm going to have x values and y1 values. And I'm going to be plugging in something in 1 second. So I can't actually plug in negative infinity here. So what I need to do is I actually need to kind of just be a little creative here. How do I plug in something that is getting closer to negative infinity? Well, I can, if I really want to, just say, all right, how about negative 99? And then how about negative 999? And then how about negative 9,999? And how about negative 99,999? And so when I do this and go into my calculator, I get the following value. I get negative 0.4513, negative 0.495, negative 0.4995, and then from then on, it's just negative 0.5. And so no matter how many nines I add after this negative sign, I'm going to start getting a rounded value to negative 0.5. And that's because this function, as x approaches negative infinity, approaches an asymptote with the value of negative 0.5. So you can use tables to find limits even if you have positive or negative infinity as the limit. For questions 14 through 27, we have a plot where the domain of the function is all real numbers, so that means that all y values are accounted for. You can plug in any value. Sorry, not all y values. All x values are accounted for. You can plug in any x value, and the function is defined. And we want to make sure that we understand how to find limits for different locations in this graph. So I'll refer to all of these. So we have the limit as x approaches negative infinity of our function. So what happens as x approaches negative infinity? Well, it looks like our function just goes up and up and up forever. So the limit here is positive infinity. Then 15 asks us, what is the value of the function at x equals negative 3? So at x equals negative 3, this is a whole, and this is our actual value. So our function has a value of negative 3 at x equals negative 3. Now, what is the limit as x approaches negative 3 from the left, from the right, and then from both sides? So here, I'm going to say, as I approach negative 3 from the left, I am approaching a value of negative 3. As I approach negative 3 from the right, I'll change colors, I'm approaching this whole. So I'm not approaching a value of negative 3, I'm actually approaching a value of what I assume is negative 2. Then, as I approach negative 3 from both sides, I have a situation where I cannot approach the same value. So really, I am approaching two different values. So this actual limit does not exist. Now, to go on, what is the value of the function at x equals 1? So here we have, again, a whole and then an actual defined value. So this is a value of negative 2. Then we have x approaching 1 from the left, the right, and from both sides. So we have from the left, we are approaching a value of 0. From the right, we are approaching a value of also 0. And then as we approach both sides, we again end up with a limit that does exist because we are approaching the same value from both sides, and that is 0. For number 23, we have a function value of 4. And so at x equals 4, our function has the value, pardon me, I meant to change colors. We have the function value of positive 3. Then our limit as x approaches 4 from all sides, we have from the left side, x approaches 4, and we have again a value of 3 from the left. Then from the right, our function actually is approaching this value, which is 0. And so as x approaches 4 from both sides, we are approaching two different values. So our limit in this case does not exist. And finally, as x approaches positive infinity, it appears that we have a horizontal asymptote on this end, which we can, I guess, assume goes to an asymptotic value of -2. So these tend to be fairly easy, but make sure that you understand when a limit exists and when it does not. So for question number 28 and on here, or for the next few questions, we have a situation where we have a piecewise function, so we have two halves of this function, and we are curious if the function has a limit that exists at x equals -2. So what does that mean? That means that h of x must approach one value, at x equals -2 from both sides. So what I can do is I can just set both sides equal to each other. So I have 3x plus 2 is equal to x squared plus 3x minus 1, and this is supposed to be true at x equals -2. So what I can do is just substitute in my -2 for x. So I have 3 times -2 plus 2 equals -2 squared plus 3 times -2 minus 1. So on the left-hand side, we have -6 plus 2 equals, so -2 squared is +4, minus 6 minus 1, so we have -4 on the left, and on the right we have -3, so these do in fact not equal each other. So does our function have a limit at x equals -2? No. Our limit does not exist because these do not approach the same value from both sides. For number 29, we now have a function that has an unknown constant k. And so we want to know we want to find a value of k so that the limit of q of x exists at x equals 2. So again, both functions must approach one value at x equals 2. So I will set these two sides equal to each other, and then at x equals +2, that would turn into 3 times 2 plus 2 equals 2 squared plus k. So in order for this function to have a limit that exists at x equals 2, I need to solve for this k value. So in this particular case, I have 8 minus 4 equals k, or k equals 4. So that means that if my second half of the function is x squared plus 4, then the limit at x equals 2 exists. Now question 30 looks a little more complicated, but it's not too terrible. So we have a function that has now 3 parts. We want to determine a constant value for a and a constant value for b so that the limit of g of x is equal to g of 0, and the limit of g of x at x equals 1 is g of 1. So essentially we're going to be making a little chain of things here. So we have first, at x equals 0, we have the fact that 2x plus a cubed must be equal to 5bx plus 8. And so this is all at x equals 0. So let's go ahead and simplify this to begin with. So I have 2, I'm going to go ahead and leave it as is for now. I have 2 times 0 plus a cubed is equal to 5 times b times 0 plus 8. So I have a couple terms that go away. So this turns into just a cubed. And on this side, we have 5b times 0, so that is 0, is equal to 8. Therefore, a is equal to the cube root of 8, which is just positive 2. So that's fine. Now we have a value for a. Then, at x equals 1, we have a different situation because we have two different equations that meet there. So now we have 5bx plus 8 is equal to x squared plus 12. So going ahead and plugging in 1 for x, we have 5b times 1 plus 8 equals 1 squared plus 12. So this simplifies to 5b plus 8 equals 13. So 5b will be equal to positive 5. So therefore, b is equal to just 1. So these are the values for a and b such that these two limits exist. So this is quite simple. You're simply setting two sides equal to each other to make sure that they approach or end up at the same value at some particular x coordinate. Questions 31 through, I believe, 38 or 39, are all involving our properties of limits for functions. So firstly, if our function is defined at some particular value, then we can simply just plug in the x coordinate to our function and find the value. So in case you've forgotten, this is limit as x approaches c of f of x is just equal to f of c. So I'm going to go ahead and just plug this in. So I have 2 minus 3 times negative 2 minus negative 2 squared plus 2 times negative 2 cubed. So this is 2 plus 6, and then negative 2 squared is positive 4, so I have negative 4, or minus 4. Then I have negative 2 cubed, which is negative 8 times 2 is negative 16. And so putting all of this together, we end up with 8 minus 20, so this is negative 12. So the limit as x approaches negative 2 is negative 12 for this polynomial. For number 32, again, if our function is defined, we can simply just plug in our values. So I have, or our value of x. So I have 3 minus 5 times negative 1 cubed over 5 minus 1 plus negative 1 squared. So this would be 3, so we have negative 1 cubed, which is negative 1, so plus 5 now, over negative 1 squared is positive 1, and then negative 1 and positive 1 cancel out, so we have this over 5. So in the end, we have 8/5. So our limit for this function as x approaches negative 1 is just 8/5. So these are relatively simple so far. Let's try this one. So here we just have an exponential function that is very likely defined at as x approaches 2. So we'll simply plug in our values. So we have 3 raised to the 2 minus 4 times 2 raised to the 2 cubed minus 6. So remembering your order of operations, I'll go ahead and square this. So we have 9 minus 4 times, we have 2 cubed, which is 8. So 2 raised to the 8 minus 6. So I have 9 minus 4 times 2. Now 8 minus 6 is 2. So this is 4 times 2 squared. So 9 minus 4 times 4. Then we have 9 minus 4 times 4 is 16. So this is in fact negative 7. So our limit here is negative 7. Now, we get into some weird cases when we get to number 34. So for number 34, we have a couple different things we can do. Number one, we can kind of remember what happens when we have a function times some constant. So the limit as x approaches 0 of 12 over 15 times sine of x over x is the same as 12 over 15 times the limit as x approaches 0 of just the sine x over x. So if you recall from using our tables, we can say, so from our tables with y1 equals sine of x over x, we know that this limit right here is actually the limit. Actually, so you can either use a table or you can use a graph here. But the limit as sine of x over x as x approaches 0 is actually 1. So this would be 12/15 times 1, because the limit of this is 1. So in the end, this actually just ends up being 12/15, which we can simplify to 4/5. So if you recall in previous homework, this right here, you were suggested to memorize. So again, we will suggest that. So moving on, 35. So in this problem, we have a kind of terrible looking setup, but it is suggested to use a trigonometry identity, is what this is supposed to say, to change the numerator and use our limit that we just discussed in 34. So we're going to start with our function 1 minus cosine squared x over 4x squared. So my trig identity that I want to use is 1 is equal to cosine squared x plus sine squared x. Therefore, 1 minus cosine squared x is equal to sine squared x. So I can rewrite this function as sine squared x over 4x squared. Now I can actually rewrite this again if I want to use sine of x over x, because I can say, all right, this is actually the same as if I split it up, 1/4 times sine x over x times sine x over x, because this is sine x over x squared. So since each one of these is 1, I can just say that the limit of this whole function is the same as the limit as x approaches 0 of sine x over x squared times 1/4. So since this limit right here is 1, then this is just 1/4 times 1 squared, or 1/4. So our limit, which I guess I'll just write here, is actually just 1/4. So again, we're going to try to use this. Now we're going to say we're going to multiply the denominator by 1 plus cosine of x and simplify that denominator with some known identity. So what we're doing now is we're kind of cheating a little bit, but we have 1, so let's call this g of x, is 1 minus cosine x over 2x sine x. So I'm going to multiply both numerator and denominator by 1 plus cosine x. So this is kind of similar to when you were rationalizing. So when I do that, in the numerator I get 1 minus cosine squared x. And in the denominator I have 2x sine x plus 2x sine x cosine x. So where can I go from here? Well, in the numerator, I'm going to use my identity from the previous one, and that was, if you recall, 1 minus cosine squared x was equal to sine squared x. To say that, my numerator is the same as sine squared x. So this is all over something that includes sine of x in both. So I'm going to go ahead and factor out a sine of x. And that leaves me with 2x plus, actually I'm going to factor out a 2x as well. Why not? So I have 2x sine x times 1 plus cosine x. So this allows me to factor out one of my sine x's. So now I have sine of x over 2x plus 2x cosine x. So this is kind of ugly, but what can we do now? So what we're going to do is we're going to actually take this, and we're going to move it over here. And so I have sine of x over 2x. I'm going to factor it out one more time, actually. And so I can split this into two fractions. So I can have sine of x over x. Now we know this. Then I have 1 over 1 plus cosine x. And then I can also pull out a 1/2. So I have 1/2 times sine of x over x, and then 1 over 1 plus cosine x. So now we can start getting back into the limit part. So this right here is my g of x. So the limit as x approaches 0 of g of x, in this case, would be the same as 1/2, because I can pull the 1/2 out, times the limit as x approaches 0 of sine x over x. And we know this one, that's 1. And then we have this new limit as x approaches 0 of 1 over 1 plus cosine x. Well, cosine of x is going to be defined at 0 as 1. So this part right here, oops, terrible bracket. This part right here is equal to 1. And this part, if I plug in, so 1 over 1 plus cosine of 0, that is just equal to 1 over 2. So in the end, what I have is 1/2 times 1 times 1 over 2. So my limit in this case is actually just 1/4. So this is mostly algebra and not really too much to do with our limits, except for the part where we need to split it up into multiplying pieces that we can find the limits for. All right, so for 37, we are simply going to be using some properties of limits. So I have this function set up here. So I have the limit as x approaches 3 of f squared of x over x minus 5 minus x squared times g of x. So I'm going to break this up according to my properties of limits. So I can say the limit as x approaches 3 of f of x, and then I can square this. Then I'm going to multiply by the limit as x approaches 3 of 1 over x minus 5. Then I'm going to say minus the limit as x approaches 3 of x squared times the limit as x approaches 3 of g of x. So going through all of this, I know that this limit, actually, so this is squared. So this limit is going to be -2, and then I'm going to square it. This limit, I can just plug in a 3, so that's 1 over 3 minus 5, or -1/2, minus this limit, I can just plug in 3 again, so that's 3 squared, so that's 9, or just write 3 squared for now, minus this limit, which was given to be 5. So now I have +4 times -1/2 minus 9 times 5. And so my limit in this particular case is going to be equal to, so that's -2 minus, so 9 times 5 is 45. And we have -47. So let's continue down and look at number 38. So we know that this limit is given to be equal to 10. And we want to know what is the limit of just the f of x part. So if we know that we can break this up, we can say the limit as x approaches -2, handwriting, as x approaches -2. And if we break this up, we can say that it's the same as So we'll say 1 over x squared minus 2. And then we'll say this is times the limit as x approaches negative 2 of, now we can say this is x, and then we can say minus, actually, so this is going to be this whole thing, minus the limit as x approaches negative 2 of 3f of x, and this is all equal to 10. So going through this, I can do some substitution. So here I can just say this limit is 1 over negative 2 squared minus 2. Then multiplying, again I can do some substitution. This is just negative 2. Here I don't really have any substitution to do. I'm just looking for it. So I can pull the 3 out, however. So I have now 3 times the limit as x approaches negative 2 of f of x. And then this is equal to 10. So now I have, let me zoom in a moment. Now I have 1 over, so negative 2 squared is 4, minus 2 is 2. And then I have negative 2 minus 3 times this mess. I'll just make it a big circle right now. That'll be confusing. So we'll rewrite it. So limit as x approaches negative 2 of f of x is equal to 10. So now I just do some algebra. So multiply by 2. So I have negative 2 minus 3 times the limit. Is equal to now 20. So I'm going to add 2. So that'll be 22. And then I'm going to divide by negative 3. So I will have 22 over 3, and that's negative. And so here is my limit as of f of x as x approaches negative 2. And that's it for this homework. If you can make it all the way to 38, then you're in fantastic shape. But if not, you should still be pretty well off for the quiz.